Okay, so today we're going to start our section on related rates. So related rates are investigating how the change in one thing affects the change in the other. So for this example, we're doing a spherical snowball. So the rate of change of the volume, how does that affect the rate of change of the radius of the sphere? And we're going to use derivatives to do this because derivatives are essentially rates of change. Dy over dx, the change in y over the change in x. So we're going to use what we know about derivatives, what we know about implicit differentiation. So let's look at this example. So a spherical snowball, so as soon as you're doing questions like this, I would like to see you draw a diagram to represent every situation. Melt at 1 centimeter cubed per minute. So I know that that's giving me information about volume, okay? So at what rate is the radius decreasing? So I'm looking for a formula that involves volume and radius. So the volume of a sphere is 4 over 3 pi r cubed, okay? And then I'm always going to be given some information and asked to find some information. So this right here is the rate of change of the volume. So it's dV, the rate of change of the volume, over time, volume time. So it's minus 1 centimeter cubed per minute, okay? dV dt. How do I know that it's volume? Because the cube. It's melting, so it's decreasing. That's why it needs a negative. And I'm looking for the rate of the radius. So I'm not looking for the radius itself, I'm looking for the rate of the radius. So I'm looking for dr dt. That's what I'm looking for, and I've been given the fact that r equals 5, okay? So when you're doing a related rate application question, before you do any math, I want to see a picture, the formula that you're going to need to use to solve this, and any information that you have and what information you're looking for. So now we're going to continue, and we're going to actually apply d dt to both sides. And what d dt is the derivative in terms of t. So if I apply d dt to this guy, so I'm finding the derivative in terms of t, but I have a v here. So if you remember from implicit differentiation, we use the fact that dv times dv over dt is the same thing as d dt, because technically these could just cancel. So if I replace this with this says, hi, I'm here to find the derivative of any v's, and it's going to have the dv dt in it. Well, the derivative of v is 1. We're going to do the same thing over here. So we're going to do d dt, okay? So, but I'm finding the derivative of r in terms of t. So I'm going to need dr dt, which is technically the same thing as d dt. So now we're going to actually do the derivative. So the derivative of v, dv is 1, so I'm just left with a dv dt, equals, so finding the derivative of any r's, so 4 over 3 pi, that's just a coefficient, okay? Pi is a number, so we just treat that like a coefficient. So we multiply the exponent by the coefficient, so that's just going to be 4 pi r squared dr dt. Okay, so when you do these questions, you're not going to do this part of it. You're going to get to the point where you're just skipping from here to here. So basically what I want you to know is you're applying d dt to both sides, okay? But whenever you find the derivative of something other than t, you need a dv dt or a dr dt to make it mathematically correct. So now we're going to continue with solving this problem because I am looking for dr dt. So I'm looking for this. So what I like to do next is plug in everything that I do know. So I know dv dt is negative 1. I know that r is 5, and I have an r squared there. And I'm looking for dr dt. And now I'm just going to rearrange for dr dt. So 4 times 25 is 100, and I'm going to divide both sides. So I have minus 1 over 100 pi equals dr dt. So the rate of change of the radius is negative 1 over 100 pi centimeters per minute. Okay, and you should always, to finish the question off, you should write a sentence. So the radius, what you need to write what is actually changing, whether it's increasing or decreasing, is decreasing, okay, at a rate of -1 over 100 pi centimeters per minute. So when you're doing these related rate application problems, that is worth a mark, finishing it off with a sentence.